Hello everyone! Today I'll be talking about how to do basic graphs, the different types of graphs, what they mean, how to interpret them. And then I'll talk about how to make these graphs in Microsoft Excel 2013. This will also apply to previous versions, it's just that the previous versions will likely have different menu options and it'll look different. And the same will apply for future versions of Microsoft Excel. This can also work in different programs such as Google Sheets or the Apple Pages. It's just that these other programs might not have the same functionalities as you see here. But in our class, we'll be using Microsoft Excel 2013, so you should be able to follow along to this and be able to make the proper graphs that you need. So, what does every graph need? The whole point of a graph is to visually represent your data, to show it to the reader and simplify the trends, the patterns, the relationships that are going on in your data. Every graph must have an x-axis, this horizontal axis, and a y-axis, the vertical axis. On the x-axis, this is where we put our independent variable, the variable that we as a scientist decide as our parameter, as our main variable that we change in our experiment. On our y-axis, on the vertical axis, we have our dependent variable. The dependent variable depends on the independent variable, and we'll go over several examples of these as we go through these different types of graphs. Of course, we don't forget the units when applicable. If it's time, then I'll put days. If it's length, then I'll put millimeters or centimeters. Always, 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 if there are units, put units on the graph. You'll notice that we have tick marks here on the x and y axes. These markings are appropriately scaled. If I have on the x-axis out of 10 days, then I'll space this out 1 day, 2 days, 3 days, 4 days, 5 days, 6, 7, and let's pretend it goes out to 8, 9, and 10. If I have 1,000 days and I only have this much space to work with, I won't want to make this 1, 2, 3, 4, 5. I'll probably want to make this 100, 200, 300, 400, 500. So it is important to think about your scaling. You also want to have it evenly spaced. I would want this to say 100, 200, 300, not 100, 500, 1,000, and other numbers that are improperly scaled. Some of your graphs will have more than one group, and that's what's shown here. One group here is shown in X's, so this is all belonging to one group. These other dots belong to another group. These groups can be represented here and can be distinguished here in this key. So keys are only as necessary if you have multiple groups. The key is so that you can distinguish between the different groups. And so we know that the dots here are for group A, and the X's here are for group B. And of course, we always have a title for our graph. The title is a brief description of what you're showing in your graph. Contrast the title with legend. A legend is a description of the information that the graph is showing. So a title is a bit more general. It's still descriptive. It's telling you what the graph is showing, but the legend tells you the results of the graph. So I'll go over good examples of this in the coming slides. Just a note, in Excel, they call the key the legend. But I'm going to be stubborn with Excel and not go by their terms. The key is what distinguishes the groups. The legend is our description of our graph. So these are the key components of a graph. Let's go over our first type of graph, the bar graph. It's called a bar graph, very obviously, because there are bars here on a graph. And these bars can be easily compared to one another. So what we're showing here, as explained by this title, amount of food eaten by canaries based on diet type. So here we have 3 diet types, as noted here on the x-axis. Diet A, Diet B, and Diet C. Canaries were fed one of 3 diets, and their food intake was monitored for 3 weeks. So after 3 weeks, we looked at how much food they ate per day. Canaries in Diet A ate this much per day, grams per day. Canaries in Diet B ate this many grams per day. Canaries in Diet C ate this many grams per day. Based on the graph, something that no one can argue with, it's very clear that canaries who ate diet A ate the most grams per day. They ate approximately 6.8 grams per day. This is higher than the canaries in group B. This is higher than the canaries in group C. This is very clear to see. So what we can see in a bar graph are we can make simple distinctions between groups, between categories. On our x-axis, we have categories. These are letter or words. These are written things that aren't numbers that are defining what our groups are. So diet A, diet B, diet C, these are distinct categories that we can compare. And we're comparing that as in terms of food intake grams per day. So on the x-axis, we have categories. On the y-axis, we have these continuous numerical values, anywhere between 0 and 7 grams per day. Could be anywhere in between. Could be 1.1, could be 5.9, anything in between. That's what makes it continuous. Okay, so again, we can easily compare this on a bar graph, the diets of the canaries and how much they ate per day. Our simple result, is that canaries ate more under diet A than in the other diets. An interpretation of that result would be that canaries preferred to eat diet A. Because they ate more of diet A, we can conclude that they preferred to eat diet A. That's one conclusion, and it's important to distinguish results from conclusions. Results are not arguable. It's not arguable, very clear from the data, in fact, that canaries ate more from group A. It is arguable that the canaries prefer diet A. We can't get into the heads of canaries and ask them directly which food did you prefer. We're only assuming this based on food intake. So if we assume that food intake is a clear indication of preference, then yes, we can conclude that canaries prefer diet A. But what if diet A was low in nutrients and the canaries had to eat more of diet A in order to get more nutrients? Then in fact, it's not so much a preference as much as it is for survival that they need to eat more of diet A if there's not enough nutrients. So this is just a good example of why it's important to be careful of what conclusions you make based on the results, and making sure you have proper controls. If we have that these diets, diet A, B, and C, all have the same amount of nutrients, then we've controlled for amount of nutrients, then we can more clearly conclude that canaries prefer diet A. So again, bar graphs, we have categories on the x-axis. Here we measure something continuous on the y-axis. This shows clear comparisons between groups. Histograms look very much like bar graphs, but they are not the same as bar graphs. Bar graphs, we're making comparisons between different groups, and not that we can't make comparisons here in a histogram, but the clear distinction for a histogram is that in a histogram we're looking at distributions. In this case, we're looking at the distribution of student scores on quiz 1. So we have a population of students, and we want to see what scores did they get on this exam. How many got a certain score? In this quiz, there were a maximum of 10 points. Students could have gotten a score of 0, or a score of 1, or a score of 4, or a score of 7, or a score of 10, anywhere in between, but not anything like 1.1, or 5.9, or 7.7. They could have only gotten one of these 11 scores. So even though these are numbers, they're not continuous. They're actually discrete. Discrete meaning they're not divisible, or there's nothing continuous about them. They're discrete, so they're basically like categories. Just like those groups of diets those canaries are on, these quiz scores are pretty much like categories. So even though they're numbers, we're going to treat them like categories. Here on the y-axis, we have number of students. So for distributions, the y-axis is always going to be number of something. So in this case, we have students. So based on this graph, we can say one student got a score of 1, 2 students got a score of 3, 4 students got a score of 4, 4 students got a score of 7, 2 students got a score of 9, and so on. Based on this graph, we can also see how many students or how many individuals we have in this entire population. if it wasn't given to me just based on this graph, I can calculate it. If I count how many students there are total, if I add all this up, it should equal 24 students. So I know that 24 students took this quiz, and this is the spread. This is, this is the distribution of those students in my class and their quiz scores on this particular quiz. So histograms, they show distributions over a range of values. Here, even though these are numbers, it's still treated as categories. And then on the y-axis, we have number of students. Histograms are not bar graphs, they show distributions. Line graphs. Line graphs are really good for showing progression. So more often than not, the x-axis will be some form of time. Seconds, minutes, hours, days, months, years. The x-axis will most likely be time. What's important to note is that, yes, these are also numbers, just like before, but these are predetermined numbers. We're choosing to take a measurement on day 0. We're choosing to take a measurement on day 1, day 2, and we're evenly spacing it, 1, 2, 3, 4, 5, 6, 7, and so on. We're not doing 1.3 or 3.9 or 4.3. We're not choosing anything in between. So even though these are numbers, these are not continuous. So again, they're like categories. But since we're showing a progression, we're going to use the line graph. In this example, we're looking at male and female mice body weight changes over 1 week. So here, it's a little more complicated. And in this example, I'm showing you groups, so we'll need to use a key. Just a note, groups can be used on more than just line graphs. They could be used on bar graphs. They could be used on scatter plots. So I'm just showing you here how to do groups in a line graph. Again, male and female mice, body weight changes over 1 week. Over 1 week, since we're measuring daily, they're weighed daily, we're looking at their weight on day 0, day 1, day 2, and so we can see their measurements here. Since we have both male and female, we need 2 different lines. 1 line for males here in blue, 1 line for females here in red. And on the y-axis, we have body weight in grams. Male and female mice were fed a standard diet, so that's one of the controls, and they're weighed daily. One clear thing that we can see from this graph is the progression upwards. So we know that both male and female mice, as time passes, they increase in weight. Yes, they don't start out at the same weight, but both increase in weight. So there's this upward progression. We'll talk about what that means later. We can also make a comparison now between the male group and the female group. Clearly, the male group weighs more on average than the female group. So we can make comparisons like that. We can also make comparisons on rate. Because our x-axis is almost always time, and then we're measuring something else on the y-axis, we can look at a rate of change. So we can look at the change in body weight over time. So an interesting question that we can ask is, for example, when did male mice increase their body weight the fastest? Looking at these lines here between the dots, we can look at the slope of these lines. The slope of the line indicates rate of change. And if we want to know what it increases the fastest, we want to find the steepest increase. So looking at males, the blue line, the steepest increase happens between days 1 and 2. Male mice increase their body weight the fastest on days 1 to 2. We can ask other questions based on rate, looking at this, and again, that's just by looking at the slope of these lines. And we can even see that the male and female mice gain weight at approximately the same rate. I could calculate it by finding the slope of these lines and seeing what the rate of change is, and then making the comparison. What you'll notice again on these line graphs, on the x-axis we have time, and what we do is we connect the dots. We connect the dots for these groups. So for the female group, say start out here, next day they're here, so I connect the line. Next day they're here, connect the line. I'm not making a line between the first and last one. I'm connecting from dot to dot to dot to dot. You connect the dots on line graphs. This will be a contrast from the next graph that I'll show you. Connect the dot on line graphs when you're showing a progression. The last graph that I'll talk about here is the scatter plot. Scatterplot, again, visually similar to the line graph, but it is not the same thing. Line graph, if you recall, let me go back. Line graph had time on the x-axis. We're showing a progression. Here we're looking at changes in body weight. In scatterplots, we're not looking at progression. This does not have to do with progression. We're looking at relationships between two variables. What's really interesting about scatterplots is that unlike these other graphs that we've been talking about, on the x-axis and on the y-axis, we have continuous numbers, not discrete numbers, not categories, continuous numbers. So here in this example, we're looking at the relationship between exam scores and time spent studying. On the x-axis, we have time spent studying in hours. On the y-axis, we have exam score. Each of these dots represent a student, an individual, a subject, whatever you want to call it. So this is one student. This student studied for 2 hours and got a 10% on their exam. This student studied for 8 hours and earned approximately 65% on their exam. The thing is that this x-axis is a continuous variable. We, as the scientists, are not deciding what the number is. It's just that we don't decide what the number is. We just see that this student studied this many hours, and so we mark their score. So because of that, we're not deciding what is here on the x-axis. We can see that maybe someone studied for 2 hours, maybe someone studied for 3, someone studied for 4.4. There's no distinction in we as the scientists don't choose how many hours these people study. It's just that it can land wherever it goes. So the time spent studying in hours, this is a continuous variable. It is possible to get 3.3, to get 6.9, to get 8.1. Any of these are possible. Okay, so again, we're looking at relationships between exam scores and time spent studying. Very clearly, you can see this trend that the more time you spend studying, the higher score you'll get. So this is a direct relationship, and we'll talk more about this in a second. Student scores were directly related to the amount of time they spent studying. There's a relationship between time studying and exam score. I keep using the word relationship, or I can use the word correlation. Time spent studying is directly correlated with exam score. This is not causation. If you study more, you will likely score a higher score, but it won't be guaranteed that you'll get a higher score. So this is not a guarantee, this is not causation, this is only a correlation. Let me show you 2 good examples of this. Let us pick these, let's go with these 2 students. Okay, so this student here studied for 7 hours. This student studied for 7 hours and earned a 55%. This student studied 7 hours and earned an 82%. So even though they studied the same amount of hours, they got very different scores. So again, no guarantee that if you study a certain amount of hours, you'll get a certain score. On the flip side, this student here studied approximately 6.5 hours and earned approximately 64%. This student studied for 9 hours and got about the same score, 64%. Even though this student studied more, they didn't earn a higher score. Again, these graphs are showing relationships, correlations. It's more likely that if you study more, you'll get a higher score, but it's not guaranteed. So let's practice with one example. You're measuring growth, the change in height, of a plant called Arabidopsis at 2 different temperatures every day for a 5-week period. A lot going on here in this prompt, so let's break it down again. You're measuring growth, change in height, of a plant at 2 different temperatures every day for a 5-week period. So I want to know, when you graph the results, what will be put on the x-axis? What is your independent variable that you will put on the x-axis? Is it the time when the growth is recorded? Is it the temperature at which the plants are grown? Is it the species of the plant? Or is it the height of the plant? Oops, I've kind of given it away. Let me move this to the side. you didn't see that. Okay, let's do this again. So you're measuring growth. Change in height of plant at 2 different temperatures every day for a 5-week period. What will you put on the x-axis? What will you put on the y-axis? Let's start with the easiest one. You're measuring growth. Whatever you measure as a scientist, that's generally the dependent variable. Dependent variables go on the y-axis. Dependent variables go on the y-axis. So you're going to put height here. Height, let's say in centimeters. So that's growth. Height of the plants will go on the y-axis. But what will you put on the x-axis? We have 2 different things that we can put. We have temperature. That's something that we are controlling for. And we're measuring them every day. That's also something we're controlling for. So is it temperature, the temperature at which plants are grown, or is it the time when growth is recorded? Whenever we're looking at progression, if we're taking multiple time points, if we're taking multiple measurements at even time points per whatever given amount of time, in this case a 5-week period, we will want to put time on the x-axis. So time goes on the x-axis, growth, height, goes on the y-axis. Where does temperature go then? Temperature will go into 2 different groups. So that means we'll need a key. So, time, this is what I tried hiding from you. Time goes on the x-axis, time in days. Height will go on the y-axis. We'll need a key for the 2 different groups, for the 2 different temperatures. So, we'll have our key here. Here in blue, I'll make, let's say, a lower temperature, 15 degrees Celsius, and a warmer temperature, 20 degrees Celsius. That's just completely arbitrary. And then we'll have 2 different lines. Let's say the 15-degree group increases in height over time like this, and let's say the 20-degree group increases in height over time like that. Just a guess of what it might be. But this is roughly what a graph based on this prompt should look like. Of course, you'd want to add the title and the legend, but these are the basics of what we'll put here. So again, let me reiterate: if we take a measurement at specified times per day or per hour or per minute, whatever, if we're taking time points, we want to use a line graph. So this will be a line graph, and we're going to use 2 different groups to show the 2 different temperatures. More about scatterplots. We need to talk about graph relationships. I mentioned how there was a direct proportion, a positive relationship. The more time you spend studying, the higher score you'll get. That's called a direct proportion, or a positive relationship. Positive meaning it's going in the upward direction. As one amount increases, another amount increases at the same rate. The higher the value of x, the higher the value of y. Let me give you another example. Say we're looking at the progression of animals, of this dog, its growth over time. So over time, as time increases, growth increases. As time increases, growth increases. That's a direct proportion, a positive relationship. The opposite of this would be an inverse proportion, or a negative relationship. So it's a downward trend. So on a graph, it wouldn't, instead of going upward, it would be going downwards. When the one value decreases at the same rate that the other increases. So when x increases, y decreases. The higher the value of x, the lower the value of y. In this example, let's say this dog stands right next to the bulb. When this dog is standing very close to the bulb, this bulb will appear very bright to it. So, very close to the bulb, high brightness. Small distance, high brightness. Let's say the dog moves farther away. Now the bulb won't appear as bright. Increased distance, less brightness. The dog goes really far away, increase distance even more, decrease brightness even more. So the higher the value of x, the lower the value of y. That's a negative relationship or an inverse proportion. You saw those lines on, let me back up. You saw this line on the scatter plot. Note that this line is not like on a line graph. We're not connecting the dots here. This line is called a line of best fit, or a linear regression. The linear regression is meant to show a trend on the graph. It's not connecting the dots, it's not showing a progression. We're showing a trend, a relationship. To find this line of best fit, well, what the computer does for us, because for us to do it ourselves would be complicated, we're trying to minimize the sum of the squared deviations. So here are our data points, this green dot here, 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 here. We want to find a line where the distances between the line are minimized. So this is, the sum of these distances are as small as possible. That's what a linear regression, that's how a linear regression is calculated. But of course, luckily, we have our computer program to do that for us, and then we can get an equation of that line, a linear equation that defines what this line is. Hopefully you remember this equation from algebra: y equals mx plus b. Y representing the y variable, x representing the x variable. M stands for slope, rise over run. So if it's positive, it's going to go up, rise over run. If it's negative, it's going to go down. So it would be a line going this way. If it were 0, it should just be a straight line. B represents the y-intercept. So if this intersects with the origin, 0, 0, B should be 0. If it intercepts over here, this might be 3 or 4. So B is the y-intercept. When we get our linear regression on Excel, we can also not only get our linear equation, but we can also get an R-squared value. This is, again, obtained by calculating the line of best fit, our linear regression. What the R-squared value means, it indicates the strength of correlation, the goodness of fit, or the degree of relatedness. The R-squared value ranges between 0 and 1, so it's going to be a decimal, most likely. And this also reminds us that correlation does not equal causation. For example, if our R-squared value equals 0.85, what does this mean? This means that 85% of the total variation in y can be explained by the linear relationship between x and y. So 85% of the variation of those dots, let me go back, 85% of the variations in these data points can be explained by this line. The other 15% can't. The other 15% of the total variation y remains unexplained. So 85% is pretty good. That means we have 85% confidence, so to speak, that our line fits our data. That there's a high strength of correlation. So if we want to safely say that there is a trend in our graph, if we want to safely say that there's an upward trend that makes sense, that these two variables, if we want to say that these two variables are related to one another, we want a high R-squared value. Of course, we don't get to choose. It's just based on the data that we have. But if we want to say it's strong, we want a high R-squared value. Again, the highest R-squared can equal is 1. 1 would be a perfect correlation. So here are some guidelines on the strength of relationship. These numbers are debatable. These are not set in stone, and your instructors might say something different, and other people say other things too. But these are just general guidelines. If you have an R-squared value between 0.7 and 1, say 0.7 to 0.99, this is a very strong relationship. You would say that your linear regression strongly matches your data. If you have a value between 0.5 and 0.7, you'd call that moderately strong. Between 0.3 and 0.5, you'd call that a weak relationship. Between 0 and 0.3, you'd pretty much say there's no relationship at all. So use these values as a general guideline to see how strong your relationships are. Let's look at some examples. Here is a graph taken from Excel. This is a scatter plot. We've taken our data, we have our data points plotted here, and this line is not connecting the dots. It's just closely matching the dots as best as possible, minimizing the distances between the dots and the lines. We have our linear regression, our linear equation here, y equals 2.0555, x minus 0.1682. And our R-squared value equals 0.9909. Based on all of this, what we can say about our data, because there's an upward trend, because this slope is positive, we can say there's a positive correlation. So just simply based on this upward trend, based on this positive slope, we can say there's a positive correlation or a direct relationship. Because our R-squared value is so high, this is a very high value, 0.99, it's almost 1. Because our R-squared value is so high, we can say that this data is very strongly predicted by the line of best fit. So put it all together, there's a positive correlation that is very strongly predicted by the line of best fit. Positive correlation because of this, the slope. It's strongly predicted because of our high R-squared value. So it's important to have both. So we'll see that when we graph in Excel, we want to have both values displayed. Here's another example. Here we have a negative slope, negative 2.2182x, and our R-squared value is 0.8239. Here's our line of best fit shown here. You can see it's a downward trend, so very clearly it's a negative correlation. It's an inverse relationship. There's an inverse relationship that is still strongly predicted. 0.82 is still pretty high. There is a negative correlation that is strongly predicted by the line of best fit. Finally, here in this last example, we have an R-squared value of 0.028, and I didn't even bother put the linear equation because this slope is basically nothing. So because the slope is basically 0 and the R-squared value is basically 0, there is no correlation. There's no relationship between these two variables. If we were looking to see that these two variables were related, we can safely say they're probably not related. Okay, so that takes care of what each of these graphs are. Now we can move on to how to make each of these graphs on Excel. So I've provided for you these graphs already filled in, or not graphs, but these charts, tables already filled in with different values so that we can graph the different types of graphs. So if you remember, our bar graph was regarding canaries and their diet type. So here, I'm always going to put the x-axis, the independent variable, I'm going to put the independent variable in this first column, and I'm going to put the dependent variable in this second column. This is mostly for me, the way I label it, and you'll see why. Just so we can keep things in order. So the diet, that's our header. There's diet A, diet B, diet C. Then for our dependent variable, food intake, don't forget units, grams per day. 6.8, 4.9, 6.1. Note, I'm not putting 6.8 and adding the grams per day. I want these numbers to stand on their own. That'll be important for the graphing part. So, if you recall, this is for a bar graph. I have categories for the x-axis, and I have numbers for the y-axis. I'm only going to select the numbers, just these three numbers here, to start graphing. I'm not going to select the header here, just the numbers. Go to Insert, and I want a bar graph. Excel, again, they're funny. They call it a column chart. Here's a bar, but it's horizontal. I don't want a horizontal chart. I want something vertical. So I'm going to click on Insert Column Chart. Click on this first one, 2D column, clustered column. It's the simplest one. Let's go for that. I click on it, and now here's my chart. I want to make it a little bigger just so we can see it. There we go. Great. We have our chart here, our graph. Here is diet A, diet B, diet C, food intake on the y-axis, diet on the x-axis. But none of that is labeled, not even the title. So how do we get these titles? We don't really have the proper labels here. It says 1, 2, 3, and we want it to say ABC. How do we get this to put in the proper things? Let's first change this 1, 2, 3 to ABC. To do that, right-click on any of these data, any of the bars. It does not matter. So I'm going to right-click on one of the data points, select data. Let me do that again because this is really important, and we're going to do this a lot in most of these graphs. Right-click on the data, select data. Here you can edit information about your data source. I want to edit my x-axis, the horizontal category axis label. I'm going to click on Edit. It brings me to this little window here, Axis Label Range. I'm going to click on this selection button. And now, if I move over, I have a plus cursor. This plus cursor I can use to select the labels that I want. I want to select A, B, and C. So I'm going to select those three. Click on the select button again, hit OK, and you'll notice that on my chart it now says A, B, and C. And that's great. We've changed our labels. So I'll hit OK. You see here that the chart title is already displayed, but the axes titles aren't displayed. I can change what titles are and aren't displayed if I click on the chart, and then this plus sign appears on the right, chart elements. It might also appear up here in chart tools, maybe in format, but we're going to go the easy way. Click on the chart, and then click on this plus button. I want to select axes titles. Chart title is already selected, and that should be good. So our chart title, if you recall, we are looking at the amount of food eaten by canaries based on diet type. On the y-axis, this is food intake, grams per day. On the x-axis, we have diet. There you go. Here we have our amount of food eaten by canaries based on diet type. If I wanted to, now I could add this into a Word document. Let's say I open up a Word document. Just open up a blank document. Go back to Excel. Click on the graph, and I could copy it. Right-click on it, copy, or Control-C, whatever you prefer. Go back to the Word document. Right-click, paste, or Control-V. There we go. Okay, and now there's my graph, and then I can type in my legend below here. Canaries were fed one of 3 diets, and their food intake was monitored for 3 weeks. Canaries that ate diet A consumed more food than those in diet B or C. And I can save this, print it, email it, do whatever I want with it. And you can do this for the rest of the graphs that we make here in Excel. So let's go back. Okay, so we've made a bar graph. We've made a bar graph. We found out how to change the x-axis labels, add the titles for the axes, add our main title, and now let's look at how to do our other graphs. So on this next tab here I have histogram data. For the histogram data, recall that we're looking at quiz scores and number of students. Histogram looks at distribution. So the quiz score, even though it's numbers, I'm still going to treat it as categories, so I'm not going to touch this yet. Number of students, there's 0 who scored 0, 1 who scored 1, 2 who scored 3, and so on. This is the data that I want. So I'm only going to select the data, the numbers of number of students. So select that only. Insert. This is a histogram, but it looks just like a bar graph. So I'm still going to select column, this first one. I know on histograms, the way we showed it, the spacing was much closer, but don't worry about that. That's just a minor cosmetic issue. If you're more advanced, you can fix that later. But this graph looks great for now. So let's now modify our chart. Okay, so again, there's some things that we have to change here first. We don't have a title yet, we don't have axes labels, and you see the x-axis is improperly labeled. It says 1 through 11, it should say 0 through 10. So to change that, do you remember? Right-click on any of the data, select Data, click on Edit Horizontal Category, Axis Labels, click on our Select button, highlight the numbers we want, the category labels we want, 0 through 10. Hit the select button, and now it's changed. 0 through 10. Hit OK. We need to add our axes labels, so click on the plus button, axes titles. Change our main title to distribution of student scores. on quiz 1. Our y-axis label is number of students, like on any distribution it should be number of something. And on the x-axis, 0 through 10, this is referring to quiz score. And there you have it. There is our histogram. Okay, so we've done a bar, we've done a histogram. Let's move on to our line graph. Here on our line graph, we're going to learn how to do a line graph, and we're also going to see how to add more than one group and how to use a key, or what they call here in Excel a legend. So here I've already written it out for you. We have days 0, 1, 2, 3, 4, 5, 6, 7, and we're measuring body weight in grams of males and females. Male data is here, female data is here. Let's just start out by plotting a line graph of only the male data. So I'm going to select the male data here. That's selected. Insert, go over to our chart area. Line graph is here. Insert line chart. Not this one. This is for later. That's scatter. This one here. Insert line chart. I'm going to select this second one down, line with markers, because I want to see the data points at each measured time point. So I'm going to click on line with markers. So here is our line for males. It's not labeled yet, so we're going to have to work on that. The days are wrong, so we're going to have to change that too. And the axes aren't labeled. So let's start with changing the x-axis as we've done that before. So hopefully you remember, we've done this twice already now. How do you change the x-axis labels? Right-click on any of the data points. Click on Select Data. Edit horizontal axis labels. Click the Select button. Highlight the numbers you want for the categories, 0 through 7. Click again. Hit OK. And it's changed. Stay here in this Select Data screen. Because right now, Series 1, this is referring to males. We want to rename it. We want to change Series 1 to males. So I'm going to click on Series 1 and click on Edit. The series name, I could just type in males. That's fine. Or if you're lazy like me, I don't know how lazy this is really, but click on the Select button, click on males, hit the button again, and hit OK. And now it's changed to males. I know the key isn't showing yet, but we'll get to that later. But trust me, see here, it's not Series 1 anymore, it's males. Now we want to add the female group. So let's add a group. Series name, again, you can type in females, but I'm going to select it. Series values, we're going to select all those female values. So click on the Select button, highlight all the female values, click on the Select button again, hit OK. And now we have males and females. Females are shown here in red. But we don't have a key, so let's get out of this. It's all good now. So hit OK. Click on the plus button. Chart elements. We need our axis title, so let's add that for now. We need our chart title, we need that. We need our key. It doesn't say key here. Again, Excel is weird. It's really, they call it a legend, so we'll just click on legend. But now we have males here in blue, females here in red, and both our groups are shown here on the graph. And they're labeled. Great. Now we know what's what. So now we can go on to change the rest of our graph. We were looking at male and female body, female mice, excuse me, body weight changes over 1 week. The y-axis was body weight in grams, and the x-axis was time in days. And there you go. There's our line graph. Again, the way we added groups here, you could do that for a bar graph, you could do that for a histogram, you could do that for a scatter plot. It's done in the same basic way. All right, now let's move on to scatterplot. Again, scatterplots, when you add the linear regression, look like a line graph, but they're not the same thing, and they're done in very different ways. Scatterplots, like I said, because the x-axis and the y-axis, because our independent variable and our dependent variable, they're both continuous numerical variables. We're going to select not just this column of data, we're going to select both columns of data when we make our graph. So Make sure your x-axis, your independent variable, is in the first column, and your y-axis, your dependent variable, is in the second column. I've highlighted only the numbers. Insert, click on Scatter. I'm just going to select this first one. I don't want the lines yet. I'm going to add the lines later, and these lines don't look right at all. So click on the first one, Scatter. And here is my chart. What's great is that these x-axes and y-axes scaling, it's all proper. Nothing, I don't have to change anything. The time spent studying is between 1 and 11, and this is between 0 and 12, so that's good. The exam scores are between 0 and 100, 0 and 100, that's good too. We just have to label the axes. So let's do that real quick. Click on Chart Elements, Axes Titles, Chart Titles checked off. This is relationship between exam scores and time spent studying. Our y-axis is exam score, percentage. And our x-axis is time spent studying in hours. Okay. So, there. This on its own is a workable scatter plot. But, again, we can get a line of best fit, a linear regression, to tell us even more about our graph. How do we get that line? There are two ways to do it. You can click on the data points, or you can click on this plus sign and click on Add Trend Line. But what I'm going to do, since it doesn't automatically show you all these other options, what I'm going to do is click on one of the data points and right-click on it, like I've done before. Rather than click Select Data, I'm going to click on Add Trend Line. So again, let me show you that. Right-click on any of the data points, Add Trend Line. So now this window pops up. I want a linear regression. These other regressions, pretty fancy stuff. We don't need any of that for our purposes. If you take other more advanced classes, you might use them. Not here. So we're going to use our linear regression. We also want to display our linear equation on the chart, so click on that. And display the r-squared value. Check that too. And now I can close out of this. Here you can see this dotted line represents our linear regression, and here's our information: the y-squared, the line equation, the linear equation, and our r-squared value. Let me make this larger for you so you can see it. I can move this anywhere on the chart so it's out of the way of the graph. But here we have our linear equation. Y equals 7.8156x plus 7.2732. So here's our slope, 7.8156. Our r-squared value is 0.7728. So based on the slope, based on this upward trend, we can say that there's a positive correlation. There's a direct relationship. Based on the r-squared value, 0.7728, this is fairly strong. It's pretty strong. So there's a strong correlation, a strong positive correlation between time spent studying and exam score. So with pretty high confidence, we can say that the more time you spend studying, the higher score you'll get on an exam. And that's what we concluded already when we looked at this graph before. But now we've confirmed this with numbers, and numbers, as you know, are good. They're good to have in science. So that is how you do a scatter plot with a linear regression, and how you display the linear equation and the r-squared value. The linear equation will also be useful if we want to predict values. Let's say I wanted to know what score I'd get if I studied, what score I'd likely get if I studied for 6.5 hours. I could plug in 6.5 for x and do the math to figure out what score I would likely get, I would be predicted to get. Or let's say I would be happy with a score of 70 on my next exam. If I wanted a score of 70 on my next exam, how many hours should I spend studying to probably get that score? I could plug in 70 for y. 70 equals this, and I can solve for x and figure out that it's approximately 8 hours of studying that I need to do to get a 70% on the exam. Or I could just, spend less time doing these equations and study more. But yeah, That's how we can predict using the linear equation. We can extrapolate, interpolate values based on this equation. Okay, you can stop listening here if you are satisfied with everything that I've told you. If you want to know something a little more advanced, I'm going to show you how to do special distributions based on particular data that you might have. How to make a histogram based on particular data you have. So I made one more tab here. Let's say I took a walk on La Jolla Beach and I found 14 shells, and I decided to measure these population of shells. I found a shell, and one shell was 1 millimeter long. I found another shell, it was 2 millimeters long. I found another shell, it was 3 millimeters long. I found 3 shells, and they were 4 millimeters long each. I found 2 shells that are 5 millimeters long, and so on. I measured all these shells, I have this population of shells, and now I want to graph it and show the distribution of the population of shells that I have. How can I nicely show this? I could do it how I did the quiz scores. I could make a graph with how many shells are at 1 millimeter, how many shells are at 2, how many shells are at 3. But sometimes it's nicer and cleaner to actually group these together. Let's say into groups of categories of shell length. Let's say between 1 and 2 millimeters, between 3 and 4 millimeters, between 5 and 6 millimeters. These groups, another word for them is called a bin. So I can bin these shells into different categories of length. So let's do that. Shell length in millimeters. Let's say I want groups of 1 to 2 millimeters, 3 to 4, so pretty much a range of 2 per category. There's something's going to happen, and I want you to watch. So 1 to 2. I typed in 1 to 2, and it put January 2. That's not what I want, very obviously. So how do I stop Excel from doing that? Excel, it thinks it's smart. It thinks that, oh, you put 1-2. You want to put January 2. That's not what I want to do in this case, so I need to override Excel. So I'm going to delete this. I'm going to select the cells that I don't want Excel to treat as numbers or dates. So I'm going to right-click. I'm going to select the cells that I want and right-click the cells. Click on Format Cells. So I don't want Excel to automatically categorize it. I want to treat it as text, not as number, not as date, not as time. I want to treat it as text. Hit OK. So now when I go back to type in 1-2, or sorry, let me do 0-1, it's going to leave it alone. 2 to 3, 4 to 5, 6 to 7, 8 to 9, 10 to 11. So that's nicely laid out for me. These are my bins, my categories. How many shells fit within this category? How many shells are between 0 and 1 millimeters? If I look here, and I'm going to highlight it just for the sake of counting, you don't need to do this. I have 1 shell that fits between this category. I have 1 shell that fits in this range of 0 to 1 millimeters. How many shells do I have that fit between 2 to 3 millimeters? Between 2 to 3 millimeters, I have 2. 1 shell that's 2, 1 shell that's 3. So I've counted these. There are 2 shells that fit within this range. How many shells fit between a range of 4 and 5? There are 3 shells that are 4, 2 shells that are 5. So that's a total of 5. So a total of 5 shells fit between this range of 4 to 5 millimeters. How many fit between 6 and 7 millimeters? Here I have 3 shells. 3 shells that fit between 6 and 7 millimeters. How many shells fit between 8 and 9 millimeters? So, excuse me, how many shells fit between 8 and 9 millimeters? Here I have 2. 2 shells that fit between 8 and 9 millimeters. How many shells fit between 10 and 11 millimeters? I have 1 shell. So, again, here are my predetermined categories that I just made up, and that will make for a nice looking graph, a nice looking distribution. Shell length, number of shells. Since I'm graphing a distribution, I'm just going to select just these numbers, the number of shells. I'm treated this as a category, so I don't want that. Number of shells. Insert. Remember, it's a column chart, the first one, and here is my graph. I'm going to add, I'm going to change these numbers, because remember, 1, 2, 3, 4, 5, 6, we wanted to say these categories. So I'm going to right-click, select data, edit, select our range, and now it says our proper values here. Hit OK. Add in the axes titles, distribution of shell lengths on La Jolla Beach. The y-axis, like any distribution, is number of something, number of shells. The x-axis, in this case, is shell length in millimeters. And there is my binned distribution. And you can see this nice distribution. Shells are centering around a length of 4 to 5 millimeters. All right, that sums up what I have for you regarding what graphs are, how to do them, how to interpret them, and how to plot them out in Excel. Please let me know if you have any questions. My email address is acon@miracosta.edu. I didn't even introduce myself. My name is Azim Khan. If you have any questions, please feel free to contact me. I'll try to get back to you as soon as I can. Thank you. Take care. Have a great day.